From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. To think that you were worried about Stanford, I mean, how could you have been worried about a little thing like that? So I have graded the exams, and we'll hand them back at the end of class. I learned years ago that if you hand exams back at the beginning of class, you often end up with a hostile class. And we don't want a hostile class, so we'll wait to the end. So we will actually stop a little early today so I can hand them out. The last class we were talking about phase shifting interferometry, and so we want to finish that up today. And so let's, I guess it's been a week since we talked about this, so let's kind of review for just a minute. We say we have some interferometer here, and in this case we have a little Twyman grain, and we have a CCD array looking at the interference pattern, or some detector array anyway, interfaced to a computer. And the computer will read out the array, and also it will cause a phase shift between the two interfering beams. And we looked at various possible phase shifters, and we said probably the most common one was mounting a mirror on a PZT, and to move the mirror along, changing the path length, and hence changing the phase difference between the two interfering beams. And we said that by looking at 3 or more frames of data here, as we change the phase difference, we can calculate the phase difference between the two beams as a function of position. And we saw there are a number of equations that can be used to do this. And one equation that was fairly easy was where we had 4 steps, and we said between the steps we changed the phase by 90 degrees, and so the interference pattern, the radiance here will go as something plus a cosine and something minus sine, and then a minus cosine and a plus sine. And so we'll be taking differences, in this case I4 minus I2, and dividing that by I1 minus I3. We got the sine of the phase divided by the cosine of the phase. And we do this at each detector point and calculate the phase then at each detector point. And we said a nice thing about this, when we do the subtraction, that any fixed pattern noise in a detector will cancel out. And we do this little division at each detector point, so any gain variations across the detector will drop out. Any intensity variations across the beam will drop out, and we end up with something that's pretty low noise, and we can measure phase very, very precisely, and we could actually measure heights here in the angstrom or sub-angstrom range. And to go from phase to height, of course, depends a little bit on the interferometric setup and whether you're testing something in transmission or reflection or whatever. But if we're testing here in reflection and at normal incidence, then we know that phase is 2 pi over lambda times 2 times the height variation. And so once we get the phase here, we just divide by 4 pi and multiply by the wavelength, and it gives us the height, point by point. So that was the basics of phase shifting, what we call phase shifting interferometry. And before we go on to some new material on that, any questions at this point? Okay. Now, I don't think my voice has recovered yet from this basketball game. Certainly it's a good thing we didn't have a class on Sunday or Saturday afternoon. I would have been in bad shape. Okay. So now, let's go back here. We're changing the phase. And first thing we're going to do is to change this phase in discrete steps. And I'm seeing flashing lights up here. I assume everything is working okay, but okay. Anyway, we're going to move this mirror in discrete steps and change the phase difference between the two beams. And I have a little diagram here just to show that. So this is the mirror position. And let's say we're using the four-step method. And so if we move this mirror some location here, and then move it again an eighth of a wavelength, then the path difference would change by a quarter wave, and we would get a 90-degree phase change. So here are 4 positions of the mirror where they differ between consecutive positions of an eighth of a wavelength. And all we're saying is then at each detector point, we have some irradiance when the mirror is in this position. We have some other irradiance when the mirror is in that position, something else here and something else there. Okay? Now, and so this is how we would get our 4 steps. Now, instead of moving this in discrete steps, another thought might be, and the problem with moving this in discrete steps is that you move it, when you stop it, it takes a little time to stop. And then we begin moving it again, and you stop it. Again, it takes time. And so it'd be kind of nice if we could just take this and just move it along at a constant rate. Okay? So we wouldn't have all these starts and stops. So what happens if we do that? And so that's the next little view graph here, is that I'm just taking the mirror now and we're moving it along here such that over some period of time the mirror is going to move an eighth of a wave. And another period of time, another eighth of a wave, and so on. And if I were to look at the intensity here, this intensity would vary sinusoidally with time. And I think we can see that if I just go back here, find the right equation. Okay. If I go back here to this equation, if we plug in here that phi is equal to some constant times time, maybe some constant like omega, a frequency, times time, okay? Then this is going to vary sinusoidally or cosinusoidally with time. And so that's all we're doing here. We're moving the mirror along at a constant rate, changing the phase at a constant rate, and the intensity at any given point then is going to go along sinusoidally with time here. And now what we're going to do, and we'll see in the next view graph if this makes sense, is that our detector array is going to integrate the intensity as the phase difference between the two beams changes by 90 degrees. Integrate the intensity when it changes by another 90, and another 90, and so on. We're going to see in the next view graph that this is going to be essentially equivalent to where we just stepped the mirror. So we'll go along here. So we say, we have this intensity, some number plus another number times the cosine of the phase we're trying to measure, plus this thing here, which is going to be a constant, changing at a constant rate with time, like omega t. And so now we're going to integrate this as alpha varies from some alpha sub I minus delta over 2 to alpha sub I plus delta over 2. And so for our example here, delta would be equal to, say, 90 degrees. And so we would integrate this as the phase changes by 90 degrees, and then we'll divide through by the delta and normalize it. And if we go through this integral here, and I'm not going to do it in class, but the interested student will do it. In fact, the interested student already has done this in a homework problem, although maybe you don't realize it yet. That this will turn out to be the gamma naught, and then we're going to get a sinc of delta over 2 times the cosine. And so the only effect here is to reduce the modulation a little bit by the sync function. And if delta turns out to be 90 degrees, and I think this is part of your homework problem, you'll see that the sync is maybe 0.9 or some number like that. But it doesn't go down by very much. Now, I said you had really worked this in a homework problem, I think, before. And I think you had a problem early in the semester where you had fringes, and then you were scanning these fringes with a detector of some width. Didn't you have that problem? Okay. I mean, and this is, you know, here we're, in that homework problem, you were scanning it in space with a width, a rectangular function. And here, you know, we're doing it in time. But it's the same result as what you had done for your homework problem. And so it makes sense that we get this little sync function here. So this is saying that whether we step the mirror like this, and so the intensity will change in steps like this, or if we ramp the mirror like this, in which case now we're going to integrate the intensity as the phase changes by 90 degrees, that these two methods are equivalent with the exception that when we ramp the mirror, the contrast of the fringes goes down a little bit. But as long as we're only integrating as the phase changes by 90 degrees, this sync here is not going to change very much. And so the end result is a small reduction in contrast, but not very much. And I think to be really a little more correct in what I call these things, this is, I call the chapter what phase shifting, but this is generally what's called phase stepping. Boop, step. And this is called, well, integrated bucket or phase shifting. And it has turned out that phase shifting is what people almost always do instead of phase stepping, because in phase stepping, as I said before, you move the mirror or some way you change the phase difference. Let's say we're moving a mirror and it takes some time to stop it before you can take data. And then you move the mirror, it has to stop before you can take data. And so it takes longer to take data this way if you're stepping than it does if you're ramping it, moving along at a constant rate. So you get the mirror moving, and then you begin taking data as it moves along. The electronics might be a little more difficult, but the fact that you can take the data faster makes it the preferred way. So any questions? Difference between phase stepping and phase shifting? Okay. Well, let's go back to this equation here. And as we said here, we take I4 minus I2, so we get a sine, and I1 minus I3, a cosine. So we have here the sine divided by the cosine tangent. We'll take the arc tangent. Now, there's a little bit of a problem here. And the problem shows up in the next view graph. And let's say that the surface we're looking at, cover this up for the time being. Let's say the surface we're looking at has a tilt. And I don't show this, but let's say this goes through many times 2 pi. Okay? The problem is when we take this arc tangent, this is modulo 2 pi. The arc tangent always goes, well, and here I know the sine and the cosine, so I can look at the SIGN of the sine and the SIGN of the cosine, so I can see which quadrant I'm in. So I can calculate phi between 0 and 2 pi. But if I have a surface, if I'm measuring something where the phase varies many times 2 pi, I get confused once I go through 2 pi. And if I were to measure that surface, what I would see would be a surface like what I have here on the left. It will go up to 2 pi, down to 0. Up to 2 pi, down to 0. You know, because that's the way I'm calculating the phase, modulo 2 pi. And so some way I have to correct for these discontinuities here and go from here to here. And so how we do that is the following. So what we're saying here, we're doing the arctangent modulo 2 pi. I'm going to put a restriction on the phase difference between adjacent pixels. And let's say that the phase between adjacent pixels changes by less than pi. Okay? And so that's a half a wave optical path difference. If I'm looking at a surface at normal incidence, that would be, what, a quarter of a wave. And so if I go through here and I look at the phase difference between adjacent pixels, I'm okay until I get right at this boundary. And suddenly the phase difference between adjacent pixels is very close to 2 pi. And say, oops, something's wrong there, because the slope of whatever it is I'm measuring is, I had the restriction, I couldn't change by more than pi between adjacent pixels. And so what we do is we would trace this path, finding the phase difference between adjacent pixels, and whenever the phase jumped by more than pi, then we would do something here to add or subtract 2 pi, and so the difference is less than pi. So we go along here, and we see that this is greater than pi, so we add 2 pi. So that will bring that up here. And so as we keep going, we're going to be integrating up here. We're going to get a line that goes up there. And then suddenly we're going to have like a 4 pi change here. And so now we're going to have to add 4 pi to bring this up. And finally we're going to get to something that looks like this. And this is what we gave the name here at Optical Sciences, a phase integration to this, and it's sort of caught on. That's what it's generally called. And you're just adding up the phase to make sure, or checking the phase between adjacent pixels, and then adding or subtracting some multiple of 2 pi to make sure that the phase difference between adjacent pixels is always less than pi. Okay, any questions on that? Okay, if you have a surface that gives you a phase greater than pi, you can't measure it with this technique. That's what it amounts to. We just have this restriction that it's less than pi. That sets a limit on the slopes of what we can measure. And you can do tricky things of measuring it maybe at 2 different wavelengths. And again, I'll give my commercial for optical testing 513. We'll talk about that and how you can do tricky things to get around this restriction. But for optics 505, we can't look at surfaces where can't look at wavefronts where the phase changes by more than, well, pi or more between adjacent pixels. This turns out to be, it looks pretty simple here on this view graph. But in real life, it turns out to be a little more complicated. In real life, you always have a little noise in the system. And so probably your restriction of pi is, you have to make it a little less than pi, because when you add in the noise, it can't be a pi. And then you test things with obscurations in them, and so you have to work your way around the obscurations. And a lot of work has gone into developing good algorithms for doing this. And I think if you go out and you look at the companies selling commercial products in the phase shifting area, they all tell you about the phase shifting algorithm, but they don't really tell you just how they do this, how they've implemented this to make it real fast and foolproof. And even though it's foolproof, it still occasionally makes mistakes. Okay. So what we have here for a phase stepping or phase shifting interferometer, kind of summary here, we have an interferometer, and I don't care what it is, any two-beam interferometer we've talked about works, okay? And some way we have to cause a phase shift, and the most common way is mounting a mirror on a PCT. And then we have some detector array here. And some way we're digitizing that little A to D converter, getting that data into the computer. And the computer is controlling the phase shifting. So it's controlling some voltage going to this phase shifting mirror. And so it reads out the detector and moves the mirror along, normally at a constant rate. You read out the detector 3, 4, 5, 6, 7 times. Calculate the phase. At many points there you can have your detector, might be as simple as 256 by 256 detector elements. Might be 1,000 by 1,000 elements. In any case, it's doing all this work and calculating the height variation at each point, taking care of these 2 pi ambiguities, and all this happens in a fraction of a second nowadays. Computers are so fast. So now I've told you everything you need to know to start a company selling these interferometers. Okay, any questions? Okay, well that finishes off chapter 9 of the notes. And now we go on to chapter 10. And so far we've been talking about interferometry. Chapter 10 here is going to begin talking about diffraction. Of course, we're soon going to find out it's the same thing, but we're going to call it something different. So 10 is a preliminary description of diffraction. So let's say we take a point source here. It's hard to find a real point source, but we're going to have a very small source, okay? And I'm going to put something here that's opaque. Opaque obstacle. And I'm going to come over here someplace. And we put a screen over here. And so we get some shadow here. Oops. Produced by this opaque obstacle. And if we were taking a geometrical course, we would say the edges here are real sharp. But if we take into account diffraction here, we're going to find out that the edges here are not real sharp. That it's kind of a fuzzy edge here. It's not a perfectly defined shadow. And furthermore, if I start out here with a source that is monochromatic or quasi-monochromatic, we're going to see not only is the edge of this shadow kind of fuzzy, but as we look out here, outside the shadow, we're going to see some interference fringes, okay, if we have a quasi-monochromatic source. And if I were to put my eye here and look back, what I would see is that the edge of this opaque thing really is bright, okay? It's acting like secondary sources. And if we go through and calculate these interference fringes we get here, it's going to be just like having this beam going along and another wavefront coming from the edge of this shadow, and that's producing interference fringes outside here. So, I mean, the concepts of diffraction have been around a long time, and I think the first book on this was written by a person by the name of Grimaldi in about 1665 or so. And kind of, the conclusion is that the light really doesn't propagate quite like what geometrical ray optics says it should. and that the direction of propagation here is somewhat affected by these boundaries here. And this deviation from the prediction of geometrical optics is what we call diffraction. So this deviation from prediction of geometrical optics is called diffraction. And as we go through this, what we're going to find out is that, you know, this angular deviation here is proportional to wavelength, it will turn out. And so for light, the wavelength is pretty small, and so these diffraction effects are fairly small, much less than what you'd have, say, for microwaves. But they still, still are very, very noticeable. And that as we go through this derivation for diffraction, it will turn out that in the limit that we let the wavelength go to 0, diffraction will disappear. And we will get geometrical optics back again. Okay. Well, as we go through this, I mean, what we're going to do is that we're going to, go to a wave equation, and then we're going to find solutions here that satisfy the boundary conditions here. And so really the diffraction problem is a boundary value problem. And as we go through this, I mean, the math gets a little bit messy. And, but we're going to try to kind of understand physically what's happening as we not get completely buried in all this math that we need to go through. And, I don't like going through a lot of math in class, but we have no choice. We have to go through it. And the results that we're going to get here are going to be very, very interesting results. It's well worth the pain that we're going to have to go through to get to the results. So that is the end of my little introduction here. And what we're going to do now is to begin the mathematical description. And so this is chapter 11. Well, there are a lot of books on diffraction, and there's not really that much that's new about diffraction. There hasn't not much that's been new the last many, many years. So a lot of books on diffraction, and so I have to pick some book to use. And the book of choice for me is a book called Introduction to Fourier Optics by Goodman. And in spite of the fact he's from Stanford, it's an absolutely, and in spite of the fact he was Gaskell's dissertation advisor. In fact, Gaskell was his second student, it turns out. And he refers to Gaskell as his second student and his first mistake. But, but anyway, this book, I mean, it is superb. It is really very, very well written. I actually have heard him say that. Anyway, in jest, I guess. But the book there's a second edition out now, and the first edition came out in 1968. And, at that time there really wasn't anything new in the book, but it became a real big success. And the reason is that Goodman is so good at writing. He can take stuff out of Bohr and Wolf and write it in a way that anyone can understand it. I mean, it's a fantastic book. And then, so that was 68, he came out with the first edition, and then he just came out with a second edition in 96. And there are, you know, a few new things in here, but it's basically the same book that came out in 68. And it's so well written that I hope everyone here has a copy of it. And my notes, I mean, you don't even need to copy down what I'm going to write here, because I'm stealing it right out of Goodman's book for the most part. When I'm not, I'll tell you that I'm not. But you know, he does such a good job of explaining things that I will just use it. At some points, I will add a little more, you know, a little more physical interpretation beyond what Joe Goodman has there. But it's a superb book. Okay. Well, the electric field is a vector quantity, but in most treatments of diffraction, at least the initial treatments of diffraction, people treat the light as a scalar quantity. And that's what we're going to do in this course, is that we will treat light as a scalar quantity. Now, maybe that bothers you. It used to bother me a little bit. But the end result, it turns out it's much, the end results are so close to what you get if you go through all the pain and suffering of doing a vector analysis. As long as the features that you're looking at, say the diffracting aperture, as long as that's large compared to the wavelength, so maybe I should write that down. So we will, to get away with treating light as a scalar quantity, we're going to require that the diffracting aperture is, say, greater than the wavelength, a few times greater than the wavelength. And when you go to some diffraction gratings or holography, sometimes you don't satisfy that condition. But still the results are very close to what you would get if you went through the vector quantity. The orders are in the right location. Maybe the intensities are a little off from what they would be if you went through the vector analysis. But it worked amazingly well. And the second thing is that we don't want to observe the fields too close to the aperture. So, oops, diffracted fields not observed too close through the aperture. Okay. We're going to go through here, we're going to, as I said, follow Goodman's, and it's chapter 3 and 4. And I'm going to take it right out of the book, so you don't, you know, you can write down the notes if you want, or you can read the book, or you can do both, or next class you can just bring the book and follow me if you want, whatever. And as I depart from the book, I'll make comments, let you know I'm departing. So we're going to start out here, going to work with the Helmholtz equation. And so we have some disturbance here, little u of p, at point p, and it's a function of time. And we're going to write that as some complex quantity u of p. So it's a function of position times e to the minus I omega t. And of course, well, at the end we'd have to take the real part of this, but I'm not even going to write that down, we're just going to remember that. So this time dependence we know, u of p we want to find out, and u of p is something or another, but it's some magnitude here times e minus I phase. Okay? So our goal is to find out what this is. And when in doubt, you write down the wave equation, I guess. Okay? Go from there. And so del squared u minus 1 over c squared, second derivative u with respect to t is 0. Need more coffee. And, well, yeah, we know this del squared is second derivative with respect to x, and second derivative with respect to y, and second derivative with respect to z. So now we know the time dependence here, and it's really just the space dependence that we need to find. And so I'm only interested in the u of p. I'm not going to worry about the rest. And so we can plug that into the wave equation here. So slide it up. And we get that del squared plus k squared times u is equal to 0. And k is 2 pi over lambda. C is lambda nu, how we got the k squared. This is known as the Helmholtz equation. I'll draw a box around it, okay? Okay, well, so what? Well, let's keep playing. We have to go here for a while before we see the light at the end of the tunnel here, I guess. So let's go on to section 11.2. And what we're going to do here is to use Green's theorem. And really what we're going to find out is that the calculation of this quantity u that we're trying to find at an observation point, P, I guess, whatever, that this can be accomplished by use of the Green's theorem. Okay. Now the Green's theorem is covered in any book that you have in advanced calculus, and we're just going to write it down. If you want to find out more about it, I'll let you go back to your advanced calculus book if you prefer. But what this is going to be here is, we'll say let u of p, which is what we're trying to find, and g of p, which is going to be a Green's function. But anyway, let this be any two complex valued functions of position. And let S, we'll have a drawing here in a second, but let S be a closed surface surrounding a volume V. Okay. And again, I mean, you can get this straight out of Joe Goodman's book here. If U, G, and their first and second partial derivatives are single valued, and continuous, within and on S, then we have the following equation here. we're going to have this integral over the volume of g del squared u minus u del squared g integrated over the volume dv is equal to the integral over the surface of g partial of u with respect to n minus u partial g with respect to n integrated over the surface of ds. And I guess where, oops, if I can read that, partial with respect to n signifies a partial derivative in the outward direction at each point on S. So that's just a statement of the Green's theorem, which probably everyone here has seen. I don't know if you have dreamed about the Green's theorem or not, but how many of you dreamed about interference fringes last night? I don't know. Not doing well here, I guess. Anyway, the whole trick is now we're going to become very smart, with a little help from Joe Goodman, that is. We're going to be very smart in picking the Green's function and this surface S, and we'll find out that we're able to solve for the diffraction problem. We'll be able to solve for U. Okay? So the next thing is, what we'll do next is using this Green's theorem, we will now pick the correct Green's function to solve the diffraction problem. So I'll write that down. We'll now pick correct Green's function to solve the diffraction problem. Okay, and so that takes us to section 11.3, which is going to be called the integral theorem of Helmholtz and Kirchhoff. Okay. Warn you, for some reason I keep forgetting the second H in Kirchhoff, so you have to correct me when I forget that. Okay, so take some coffee here. And we will charge ahead. Go to different color ink. Okay, so what we have is that we have some point P naught. And we want to find the disturbance at point P naught. Okay? And we're going to do that by using the Green's theorem. So we're going to put some surface here, S, which has some outward normal, N. And so we're going to find a disturbance at P naught in terms of its values on the surface S. Okay? So we will come back to this drawing because we're going to have to modify it in a minute. Okay, we want to use the Green's function to do this. And so now we have to get clever about picking the Green's function. And let me just pick something at random. How's that? So let's choose as our Green's function, just for the heck of it. And also because Goodman suggested it. And a lot of people before him suggested it. So this G here, we're going to pick it as a unit amplitude spherical wave. Expanding about the point P naught. And so G at some point P1 is e to the I k R01, so the distance from point P0 to P1 divided by R01. So I'll just say that R01 is length of vector R01, pointing from P0 to P1. Okay, so this is our Green's function right there, spherical wave. Move the drawing out of the way, but we're going to bring it back very soon. Okay, now going back to the Green's function, one thing we said is that this Green's function and its first and second derivatives must be continuous within V. Okay? So what we have is this little spherical wave, G, is a spherical wave coming out from point P0. And so we're going to have an awful big problem here when P1 becomes P0, because we're going to get a zero down here. And so some way we have to exclude this discontinuity at P0. So we'll say, therefore, to exclude discontinuity at P0, we need to put a small spherical surface S sub epsilon. This is going to be inserted at about point P0. And so if we go back here for a second, go back to our drawing, what we're going to have to do here is to put a small spherical surface here, centered, well, that's supposed to be a sphere, okay, centered about P0, and this thing here has a radius of epsilon. So you can probably guess how big that spherical surface is soon going to become. But in any case, right now it's radius epsilon. And the surface area here is S sub epsilon. And spherical surface, and so we're going to integrate over this volume V prime out here. And this outward normal then is going to be like so. So anyway, so the surface we're integrating over would be this surface plus this surface, and the volume then will be what's in between the two, or V prime. Maybe I should write that down. So volume of integration is V prime. Surface of integration is S prime, which is S, what's outside, plus S sub epsilon. Okay? Any questions up to this point? Anyway. Now, this Green's function is an expanding spherical wave. So let's say since G is an expanding spherical wave, it will satisfy the Helmholtz equation. And so del squared plus k squared times G is 0. And we also have del squared plus k squared times U is equal to 0. Okay. So now we will use that, going back to our, wherever it is here, equation we had for the Green's theorem here, where we had the integral over the volume, this integral over the surface. And so we will now have, since this is true, the integral over the volume, which is V prime now, of G del squared U minus U del squared G dV is equal to, it's equal to down here, just plugging in from right here, that's equal to minus integral over the volume of G U k squared minus U G k squared dV, which is equal to 0. So that's kind of interesting. So now this messy Green's theorem becomes so it's going to become the integral over S prime of G partial of U with respect to N minus U partial of G with respect to N ds is equal to 0. And remember here, just so we don't forget, that S prime was S plus this little S sub epsilon. Okay, so moving ahead. So I'm warning you, when we get to the end, this is all going to be great. So just bear with me through this pain and suffering here. The end result will be super. However, it won't be today, but we'll get there someday. Okay. And before we win the Final Four, we'll be there. Probably long before we win it. Anyway, so if this is true, if this is true, then I can write here that minus the integral over S sub epsilon of G partial of U with respect to N minus U partial of G with respect to N ds is equal to the integral over S of the same mass. Okay? So integral over the little guy is equal to minus the integral over the big guy. Okay? Now, let's go back here. And we could write for this, for a point on the little spherical surface, we could write that, well, for a point P1 on, well, not just a little, any place on the surface here, either inside or outside here, we can write that G of P1 is e to the I k R01 over R01. And we could write then that the partial of G, and then partial of G, this point P1 on the surface with respect to n, so this is normal, is equal to, going through and doing this derivative, it's going to be equal to the partial of R with respect to n times the partial of G with respect to R. So I could say the partial of R01 with respect to n, partial of G with respect to R01. And so that's equal to the cosine, and I'm going to run out of space here, so come down here, cosine of the angle between n and R01 times ik minus 1 over R01 e to the ik R01 over R01. So this cosine here represents the cosine of the angle between the outward normal of n and the vector R01 going from P0 to P1. Maybe I should write that down as well. Again, if your hand is getting tired of writing, you can read Goodman's book. So cosine of n R01 represents cosine of the angle between the outward normal n and the vector R01 joining P0 to P1. Okay. And so for P1 on S sub epsilon, cosine n R01 is equal to minus 1. Okay, so the outward normal of the volume here, the outward normal of the surface would be this way, going towards point P0, and so this cosine here, the angle between the outward normal and the vector going from P0 to P1 would be minus 1. Okay? So now what we will have is that G of P1 is e to the I k epsilon over epsilon. So we're on this surface S sub epsilon, so G for a point on that surface is e to the I k epsilon over epsilon. And partial of G with respect to P1 relative to n is e to the I k epsilon over epsilon 1 over epsilon minus ik. Okay? Well, can you make a wild guess what we're now going to do with epsilon? Needless to say, we're going to let epsilon become small. And the continuity then of u and its derivatives at p naught allows us to write the following. So epsilon has become small, so we have s of epsilon, integral over that, g partial of u, respect to n, minus u partial g, respect to n, ds, is equal to, maybe I'll come down here, equal to 4 pi epsilon squared times a partial of u at point p naught relative to n, e to the I k epsilon over epsilon minus u naught, a u at point p naught, e to the I k epsilon times, oops, still didn't have enough space, times 1 over epsilon minus I k and in the limit epsilon goes to 0, this becomes minus 4 pi u of p naught. One thing that bothered me here. That's because I left out something right there. Does that make more sense now? So in the limit here, the epsilon goes to 0. This first guy is going to go away, and this will go away. Epsilons will cancel here. I left minus 4 pi u of p naught. Therefore, what we have, after all this pain and suffering, we have that u of p naught, 1 over 4 pi, integral over s of partial of u, respect to n, e to the I k r01, or r01, minus u partial with respect to n of e to the I k r01 over r01 ds. So we've gone through a lot of pain and suffering to get here. You have to wonder if it's worth it, but have faith it will be. Anyway, this is what we call the integral theorem of Helmholtz and Kirchhoff. And what it's doing is it's allowing the field at any point p naught to be expressed in terms of the boundary values of the wave on any closed surface surrounding that point. Maybe I should write that down. So this theorem here allows the field at any point p naught to be expressed in terms of the boundary values of the wave on any closed surface surrounding that point. So what we're going to do next here, and I'm actually going to wait till next class because I want to hand back the exams, is that next class we'll come back to this and we will go to what's called the Kirchhoff formulation of diffraction, simply by starting out with this expression here and playing with this surface here. And well, actually next class we're going to get some very interesting results. So I think with that I'll stop for this lecture and hand out the homework. And I'll say a couple of things, not the homework, the exam. And I'll say a couple of things about the exam. First off, I think throughout my history of teaching this class, my solution sheet for all exams has been pretty much one page. That's when I wrote it by hand. Now I've done it on the computer, and so now it takes 6 pages or something. But I actually had done the whole thing on a sheet of paper first in less than 1 page. So don't be surprised when you see 6 pages in a solution sheet. The average, what do you think the average was? 22? No. That was a high. No. Well, the average was 69.5. The median was 67.5. What was the high? No, not quite. I always could find something. Well, 2 people got 97, okay? And the lowest score was a 34. And, you know, with a few exceptions, I think you did reasonably well on the exam. And so why don't I hand it out here. And I think what I'm going to do, I'm going to turn off the microphone because I don't need to record on tape my mispronouncing all these names. And so we'll turn off the mic. Get rid of it.
From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. So you have homework due today. And over here on my left side, we have some old homework and exams and various stuff I'm trying to clean out of my office. So if you pick it up after class, I'd appreciate it. I guess we start off with the most important item, which is, who do we play in basketball tonight? Cal. Cal? Oh, USC. Okay, good, good. Very good. Okay. And Saturday, who do we play? UCLA. And then what happens on Sunday? You do your homework, is that? And they have the selection for the NCAA tournament, I guess, is what is actually happening on Sunday. Anyway, last class we were talking about diffraction. And right at the end of the class, we got to the integral theorem of Helmholtz and Kirchhoff. So let's write that down again. And remind you that we're following Goodman's book very closely. So if you brought Goodman's book to class, you probably don't have to write down too much here, because essentially everything we're going to say today is in his book. So we had the expression right at the end of class that u of p naught was 1 over 4 pi, the integral over this surface, which we'll soon worry about, partial view respect to n, e to the I, k, r01, r01, minus u, partial with respect to n, of e to the I, k, r01, oops, let me get that in the field of view here, divided by r01, oops, and a ds right there at the end. Okay, so that's what we had at the end of last class. Now, what we're going to do now is to go on to the what's called the Kirchhoff formulation of diffraction by a plane screen. And this is section 11.4. So Kirchhoff formulation of diffraction by a plane screen. Okay, so what we have is that at some point p naught here, and our goal is to find the disturbance of that point p naught. And over here at the left, we have some diffracting screen, okay, which I'll draw like so. And we have some light, some radiation maybe I should say, coming in from the left. So we have some wave coming in this way. And what we're going to do, we have to go through this integral here over some surface. And part of that surface is going to be this open portion here. That's how light's getting to this point. We'll call that open portion sigma here. And so what we're going to do is we're going to make a surface here that is supposed to be a circle. And hope you believe that that's a circle. Anyone doubt but what that's a circle? Okay, good. Circle here of radius r. And we'll come over here to some point on this open portion here, which I'll put in blue maybe. So this is the R01. The outward normal here is going to be like so, N. And this surface along here is going to be called S1.